18, we're going to take a look at the sampling distribution model for sample proportions and do some examples. We do have some conditions that we have to make sure that are met in order to use the model I'm going to show you. The first one, which we've seen lots of times, is that we have to have a random sample. Sometimes we don't have a random sample, so we need to be able to argue that the sample is representative of the population. So that's one of the things you want to make sure is the case. Another thing is we want to make sure our sample is large enough, which means just like with the binomial we saw before when we use a normal approximation, n times p has to be greater than or equal to 10, which would mean we have at least 10 successes. And n times 1 minus p, or we could say n times q, also has to be greater than or equal to 10, which means we have at least 10 failures. So the sample size has to be large enough, but the sample size can't be too large. We have to make sure the sample size is less than 10% of the population. And this actually helps us with the idea of independence, because we often don't have an independent sampling because we might have a finite population and we are not sampling and then putting that whatever we sample, we're not putting it back into the population. So because of that, it's not independent. So in order to still be able to treat it as though it were independent, we have to make sure that we do not exceed 10% of the population for our sample size. So as long as those conditions are met, then the sampling distribution of the sample proportions is approximately normal, with mean, and we're going to use the symbol mu with a subscript of p hat. So the mean of the p hats is p. And the standard deviation of the p hats is the square root of p times q over n, and remember q is the same as 1 minus p. So I would do this with my notation approximately normal, but remember that's what the little squiggle means, because it is important to recognize that it's approximately normal and not exactly normal. So that's what we're looking at here. Now this is on your yellow sheet, so you do have this information, but we are going to use it so much you probably won't need to refer to it on your yellow sheet. So I'm going to do a few examples. These are all on page 429 if you wanted to look there at all. I have it here as well. So this first one, back to school, best known for its testing program, ACT Incorporated also compiles data on a variety of issues in education. In 2004, the company reported that the national college freshman to sophomore retention rate held steady at 74% over the previous 4 years. So that's telling us that 74% in general of the population of students return to college for their sophomore year. Consider colleges with freshman classes of 400 students. Use the 68, 95, 99.7 rule to describe the sampling distribution model for the percentage of those students, of those 400 students, we expect to return to that school for their sophomore years. Do you think the appropriate conditions are met? So we're going to look at the conditions first. So in this problem, they're actually telling us that P, the true proportion, is 0.74. So they're giving us that as a population proportion. Our sample size is the 400 students. It says consider colleges with freshman classes of 400 students. So we're looking at a sample size of various colleges that have 400 freshman students. So I'm going to actually go through our conditions, and not necessarily in the order I gave them to you before, but one of the conditions, remember, was n times p. So if you do 400 times 0.74, and we can calculate that. I don't think I have my calculator open here. Okay, so we get 296, which is clearly greater than or equal to 10. Then we also need to check n times 1 minus p. So 400 times 0.26. So if we do that, we get 104, also greater than or equal to 10. So that's one condition met. We have more than 10 successes and more than 10 failures. So I'm not told that I have a random sample, so I'm going to have to make an assumption, and I am going to assume the 400 freshmen are representative of all college freshmen. So even though I don't have random samples, I'm going to make that assumption that they are representative to satisfy that condition. And then next I'm going to say that 400 is less than 10% of all college freshmen. So, and that's a fair assumption. We know there's more than 4,000 college freshmen in the United States. So we know that. So the conditions are met. So now I can say that my distribution is approximately normal with a mean of p, which is 0.74, and a standard deviation of the square root of p, 0.74, 1 minus p, which is 0.26, over n, which was 400. So that's all underneath the square root sign. So if we were to calculate that standard deviation, because we are going to need that, we get the square root of 0.74 times 0.26 divided by 400. So this is about 0.0219. Okay, so from there, if I were to draw out, because we were asked, the conditions were met, so we know what the normal model, the approximate normal model is, but we were asked to draw it out. Okay, that's not the greatest, but my mean is 0.74. If I go 3 standard deviations out, I should cover all of it. This should be like way down here. So I'm going to take 0.74 and add 0.0219. So I get 0.7619. I'm just going to put 0.76. And actually, I'm just going to add 0.02 each time. So this would be at roughly 0.78. 0.8. Actually, maybe I did do this. Plus 0.0219, and then I just rounded. 0.78 plus 0.0219, and then that would round to 0.81. Then going the other direction, doing the same thing except subtracting 0.0219. I kind of did it ahead of time. I got 0.72, 0.70, 0.67. So then I'm going to have 68% within 1 standard deviation of the mean. And then we would have 95% within 2 standard deviations of the mean, and 99.7% within 3 standard deviations of the mean. And that would be my 68, 95, 99.7 rule showing for that particular model. So this next question, problem 13, still dealing with the same ACT situation. Based on the 74% national retention rate described in exercise 11, does a college where 522 of their 603 freshmen returned the next year as sophomores have a right to brag that it has an unusually high retention rate? Okay, so in this problem, we have a few changes here. We're still told that P is 0.74 because it says based on this national retention rate. But this time we're given a P hat value. We're told that there is a particular college that has 522 out of 603 freshmen are returning. And if I change this to a decimal value so I can kind of compare it easier, I end up with about 0.8657. So we're comparing that to 74%, and we have a little more than 86.5%. So we want to know if this, if they have bragging rights at this college. So that means that we would need to go through again. Keep in mind that we have changed our value of N because now N is 603. So we would need to go through and check our conditions. I'm going to kind of verbally go through those on some of them. we've got, actually maybe I'll just go ahead and do that. We've got n times p, which is now going to be 603 times 0.74. And clearly this is going to be greater than or equal to 10. And n times 1 minus p, which is going to be 603 times 0.26. And we know a fourth, that's more than a fourth of 603, is still going to be greater than or equal to 10, so there's no problems there. We're going to make the assumption, so we are going to assume that the 603 freshmen are representative of all freshmen. Whether or not we can say that, maybe it's a special college. And you know, we might even want to say that we're making the assumption that this college is typical of all colleges. We might want to make that assumption too. And that may or may not be true, because depending on what type of college it is, we could be violating an assumption there. So that it's okay to make note of something like that and then go on with the problem. And we do know that 603 is less than 10% of all college freshmen. So then we would be saying that this is approximately normal with a mean of 0.74. And now my standard deviation has changed from what the previous problem was, 0.74, 0.26 still, but now my n value is 603. So notice what's going to happen. I'm dividing by that square root of 603, which means my denominator of my fraction is bigger, which means my standard deviation is going to be smaller, which is what we said when you increase the sample size. So if you look at a normal model for this, and we're going to place the 0.74, and we want to see where would we find 0.86. Well, clearly it's going to be to the right. And as a matter of fact, if I were to calculate the standard deviation, and I did this ahead of time, so I'm just going to write down, this is about 0.76 if I round to two places. This was about 0.78 and about 0.79 if rounding two places. I mean, that's, so we're looking for this. Well, clearly it's off the chart. So it's more than 3 standard deviations away. Remember how you would find that with your calculator. You could go second distribution, and we are going to do normal CDF. My lower bound is going to be 0.8657. My upper bound, I'm going to do 10 to the 99th power, something ridiculously large. My mean is 0.74. My standard deviation, and I can actually put this in without calculating it first, the square root of 0.74 times 0.26 divided by 603. That's all under the square root sign. I think I did it that way. Yep. And we get this value, which is a 13 places to the left. So the probability of getting a value, we could even say it like this, the probability of having a p-hat value bigger than 0.8657 is pretty much 0. So yes, I mean, we could say 9.9 times 10 to the negative 13. So pretty much 0. So we could say that this college definitely has bragging rights, because if this truly were the proportion, then the probability of having this many students return would basically be 0. So that means they would have bragging rights. Next one, number 18, it's believed that 4% of children have a gene that may be linked to juvenile diabetes. Researchers hoping to track 20 of these children for several years test 732 newborns for the presence of this gene. What's the probability that they find enough subjects for their study? So we believe that 4% have this gene. So that's our value of P, and they're actually going to track, they're hoping to track 20 children, so they test 732 newborns. And you might wonder, well, why in the world would they need to track that many of them just to find 20? Well, checking your condition, N times P, remember, has to be greater than or equal to 10. And so if we take N times P, 732 times 0.04, we see we get 29.28, which is greater than or equal to 10, but it's actually still pretty small. Because our proportion of success is so small, then we have to have a large sample size to make sure we have enough successes. So N times 1 minus P is 732 times 0.96, which obviously is going to be way larger than 10. So that condition is met. We are not told random, so we are going to assume that the 732 newborns are representative of all newborns. And then for the third condition, we're going to make the assumption, well, we know 732 is less than 10% of all newborns. Okay, so we're good on the conditions. So that means we can say that this is approximately normal with a mean of 0.04 and a standard deviation of, we're going to have 0.04, square root of 0.04 times 0.96 divided by 732. So if I calculate what that is, we get that this value here is about 0.0072. So looking at a normal model, move this to the other side. So if we draw out a normal model, I'm going to have 0.04 here. Now I'm looking for a value. If you look for the p-hat value we're looking for, we want to have at least 20. So our p-hat value we want to have is 20 out of 732. So I'm going to calculate that. Whoops. So that is 0.0273. That's the p-hat value we're looking for. So that helps me know then I'm going to the left when I draw that out. If I do 0.04 and subtract 0.0072, I get 0.0328. If I do that again, I get 0.0256. Now I've gone below where I'm interested in. 0.0273, I'm just going to say it's in between here. And think about what we want. We want to have 20 infants, 20 children or more. We're okay if there's more than 20, just not less. So I'm actually looking for this probability. So then I can use my calculator and I can say that the probability of having a p-hat value greater than 0.0273, and so now I'm going to go second distribution, normal CDF, my lower bound 0.0273, my upper bound 10 to the 99 works, my mean is 0.04, my standard deviation, I'm just going to use the approximate one, 0.0072, which is probably not as good as the actual. And I get about 0.9611. So there's a very good chance. What's the probability they'll find enough subjects? 0.9611. That's pretty good. So they can be pretty sure they're going to have enough subjects. And the last problem I want to cover is number 20. A restaurateur anticipates serving about 180 people on a Friday evening and believes that about 20% of the patrons will order the chef's steak special. How many of those meals should he plan on serving in order to be pretty sure of having enough steaks on hand to meet customer demand? Justify your answer, including an explanation of what pretty sure means to you. It's not too good if you go to a restaurant and order the chef's special and they say, sorry, we're out. So he doesn't want to run out, but he also doesn't want to have too many left over. So he anticipates serving about 180. So that's our value of N. I'm going to switch to blue. So N equals 180. And believes about 20% will order the chef's steak special. So that's our value of P that he believes to be true. So let's make sure that our conditions are met. So N times P is going to be 180 times 0.2. So we get 36, which is greater than or equal to 10. And that means that N times 1 minus P, which is 180 times 0.8, obviously is greater than or equal to 10 because that's even going to be bigger. So that's met. We are going to make the assumption that that the patrons, the patrons are representative of all the patrons that come, and we don't have a random sample, but we are going to assume that he serves more than 1,800 people in general at his restaurant, not on that particular evening. And we're going to assume that each of these, that this is a typical Friday evening. So I'm not writing down all those other ones, but those are other things that we would have as well. So we can say this is approximately normal with a mean of 0.2 and a standard deviation of the square root of 0.2 times 0.8 over 180. And if I calculate what that is, we get this value right here is about 0.0298. The reason why I need to know that is because if I'm going to be building my normal model, then I have 0.2, 3 standard deviations each direction. So then I already did these numbers, so we had 0.2298, 0.2596, 0.2894, and then going this way, which I'm really not going to even bother with that way, because if I want to be pretty sure that I have enough, I'm going to say 2 standard deviations above is pretty sure. So I'm using that. You just have to be able to, make your case. So that seems reasonable. So 2 standard deviations above would be at this value. So I'd be looking here. So then I have, that's the proportion. So if I take 0.2596 and multiply that by the number of customers, then that is about 47 steak. What was it? Enough steaks. So I need to make sure, he would want to make sure he had at least 47 steaks to satisfy the customer demand. So that should give you some examples of, notice every single one of these I drew a picture of the normal model. So that should give you an idea of the types of problems you are going to need to do when you are looking at sampling distributions of sample proportions.